Welcome. This is Dr. Jet, and we're going to talk today about trig limits. So the first I'm going to go over the basic forms that you're supposed to know. These are not algebraic, so they sort of have to be done numerically. And then we'll extend them a little bit, look at some more complicated examples, and we'll close with the squeeze theorem. So that's what we have here today. First, the basic limits. These are the ones that you are expected to just know. We've done some of them before. The limit as x goes to 0 of sine of x over x is 1. If you graph it, you'll see it. If you take the limit and you kind of like zoom in, it's clear. The limit as x goes to 0 of cosine of x minus 1 all over x is 0. But if you make the bottom x squared, you get minus 1/2. There's not much more to these, you just have to know them. But we can use them for more complicated trig limits. Let's take a look. Here's one. The limit as x goes to 0 of the sine of 11x over x. Now you might be tempted to think, oh, this is the same thing. Look, it's almost the same thing, but there's an 11 up here. Unfortunately, there can't be an 11 there for that to match. That has to be exactly right. And the key here is that in this limit, this x, and this x are all the same thing. It doesn't have to be called x. It could be called A or U or smiley face. It does not matter. But it's the same thing in each of those places. So, our goal will be to try to get the same thing in each of these three places. Unfortunately, this 11x is kind of stuck. You can't do anything with this stuff inside of a sign. You can't pull the 11 out. You can't cancel it or anything like that. But the other two are easier to work with. I'm going to still go x goes to 0 here. This is sine of 11x. But I want an 11x down here. How do I get an 11x? I just multiply by 11. But that's sort of cheating, because I've now changed it. There's an 11 on the bottom. I can fix that by multiplying by 11 on the top. So this is the same as that one, because it's 11, 11. The 11s will cancel. Don't cancel them. We're doing it on purpose. But it's the same thing. And now we have two pieces that are exactly the same. Now using limit laws, this 11 can be pulled out, and we get 11 times the limit as x. Well, I'm going to skip that for a second. Sine of 11x over 11x. What I'd really like to say is that 11x is going to 0. So think about it. If x is going to 0, where is 11x going? Well, it's just 11 times as big, so it goes to 11 times 0, which is 0. Now that's not enough, they have to both match exactly. So if 11x is going to 0, where's x going? 1/11th of that, it's 0. So it is the same. 11x going to 0 is the same thing as saying x is going to 0. They're the same thing. Now, that they're all the same, which means this limit is 1. So we get a limit of 11. Hopefully that made sense. That's the basic concept of what we're going to do. Let's apply it now to this one. If you look carefully, stepping back, there's a limit where this x, and this x are all the same. So I'm going to do the same kind of thing I did before. I have a 5x stuck in here. So if I rewrite this as the cosine of 5x minus 1, and I divide by, instead of x, I'm going to divide by 5x. So I multiply by 5 here to make up for the fact that I divide by 5 here. And if x is going to 0, it's the same thing as saying as 5x is going to 0. Now, I'm going to skip a step visually. I'm going to factor the 5 out already. You might want to do it in 2 separate steps, but that's what I'm doing. I'm pulling that out. This, and this are all the same. So this limit is 0. And we get 0. In this case, the 5 didn't really matter because we're multiplying by 0. These are the basic kind of extensions, but you can get even more complicated. Let's try one up here. Hopefully, it's not so complicated that your head's exploding right now. Try to think about this one. I'll give you a couple seconds to work it out. Okay, so, did you think of what to do? What I'm going to do on this one is just split it into 2 fractions. Now what would I normally have up here? a 1 and a 1. Those are the same thing, right? But I don't want a 1. I want this to be like the sine of 5x. Well, over there I had sine of 11x over x, right? That worked out okay. I want an x down here. But I can't have an x here unless I put an x on top, which I just did. That is the same as before, and each of these limits, each of these pieces is going to be a separate little limit. Let me write it out. Now this one here, we did one very much like it just before. That's going to be 5. This one, however, we didn't do. But if you think about it, this is the reciprocal fraction as having the sine of 10x over x. That one would be 10. So this is going to turn out, if you just do all the steps, to be 1/10 times 5. Hopefully that makes some sense. And one more like this, tangent of x. We don't have any tangents in our basic theorems. But what is the tangent of x? It's just the sine of x over the cosine of x. So I'm going to rewrite this remember that the limits are going to the same place. And you also have to be careful. When I split this apart, the limit laws say I can do that if this limit and this limit both exist. And they do. This limit's 1. This limit, well, that's continuous at 0. So we can just plug it in. We get 1 over the cosine of 0, which is 1. So we get 1 times the cosine of 0, 1 over the cosine of 0, which is 1 times 1, which is just 1. The trig limits we can do are all kind of like this. Now, you know trigonometry, hopefully, and you know that it can get much more complicated than this. I could have had something with a sine squared of x plus a cosine squared of x and all that sort of thing. They can work out too. Some of those are more complicated, but they all involve trig identities, and that's all you do with them. You just simplify it till you get to the 3 basic rules. That's almost everything for today. There's one more bit. It's called the squeeze theorem. It has nothing directly to do with trigonometry, but it's used for trigonometry. Suppose g of x is less than or equal to f of x is less than or equal to h of x. In other words, suppose f is bounded below by g and above by h. And we suppose that the limit of g and the limit of h are the same thing. What's that saying? That's saying this g goes to L. This h goes to L. Well, if g is always smaller, h is always bigger, f is in the middle, what is the limit of f going to be? It says that the limit of f is L. How is that useful? Well, look at this function right here. The cosine of 1 over x squared is a horrific thing. It bounces all back and forth. Near x equals 0, this kind of wobbles back and forth really, really fast. But we know the cosine of x, or cosine of 1 over x squared, is between 1 and minus 1. That means x squared times it is between minus 1x squared and positive 1x squared. And as x goes to 0, this goes to 0, and this goes to 0. So the squeeze theorem says, since this side goes to 0, this side goes to 0, and we're always in between, without having to actually do anything else, we know that goes to 0. Until next time.